In this module, we're going to discuss the basics of remote sensing. On the screen right now, you can see 3D images, some of it in false color, and we'll talk about what we mean by false color during this discussion, and some of it in real color. So we'll talk about what remote sensing is and a little bit about the electromagnetic spectrum and how this all works together. So remote sensing is acquiring information about the Earth. It could be about other planets as well, but acquiring information based upon members of the electromagnetic spectrum on what we detect, and then using that information to do analysis. This is all done without direct contact. It's done with indirect contact, and we'll talk about how that all works. So we're going to deal with the electromagnetic spectrum, a very small part of which is visible by humans, and that's this area right here, which is visible by human eyesight, from the reds to the blues to the violets at the end of the visible spectrum. There are areas that are outside our visible spectrum, what we cannot see with our eye, which are known as infrared and ultraviolet, and then there are some other members of the spectrum. As we look at this, we will deal with both visible light and electromagnetic energy, which is like light but not visible to the human eye. Therefore, when we create an image with non-visible electromagnetic spectrum wavelengths, we have to realize that we give a false color to it. So if I'm looking at this area right here next to red, what we refer to as near infrared, then for me to be able to see that on an image, I have to give it a false color because it actually does not have any color, but we will usually give it a color of red so that we can understand better. This place in the spectrum is what we know as thermal infrared, and thermal infrared is that area of the spectrum which is heat. Over on the other side of the visible light is ultraviolet, and we might extend slightly into the ultraviolets. Again, other wavelengths are also used, but those are the ones that we typically see in most of our remote sensing work that we do, is between the ultraviolets, the visible light, in the infrared. We will be using discussions such as wavelengths, but light also has a particle nature to it, which is called a photon. And this is a duality of wavelengths to represent light and also photons to represent light. Certain physical characteristics can only be explained as a photon, such as how the CCD chip detects light and other wavelengths, and some of it can only be relayed as wavelengths, such as the refraction of the spectrum in the atmosphere. So the light could be coming from something like the sun, and the sun light strikes the earth, and that light then, some of it is reflected back up to the satellite, and some of it's re-emitted. So we might have light of one wavelength coming in, but whatever is being struck by that light might reflect that up or re-emit it as a different wavelength family. The spacecraft then detects that light and then sends it to a transmission satellite that sends it back to the Earth for us to do analysis. Again, the area of the spectrum that we see, we usually break into 3 color bands, red, green, and blue. We can subdivide these bands into other color bands, so it depends if we're just doing 3 colors, which is what our computer monitors normally detect, or if we're going to do multiple bands, what we call multi-spectral. That's the visible area. Again, as I mentioned before, we have these other areas that are in non-visible wavelength. For example, radar is way down here in the spectrum. Notice the size of the wavelengths. We go up into multiple meters as wavelength sizes for like microwaves and TV and radio, to things in the micrometer standpoint. So we got to be a little bit careful on the units that we use when we discuss the electromagnetic spectrum. A similar representation, except now showing the wavelengths that we have very long wavelengths in the radio end of the spectrum and very short wavelengths in like gamma rays and X-rays part of the spectrum. This slide also shows us some of the uses. Gamma rays are normally associated with nuclear effects, X-rays with atomic effects, the ultraviolet visible in infrared, the far end of the infrared with things such as heat, and so on and so forth. You can also see that the atmosphere is transparent to certain wavelengths. That's what this area above here is showing, the transparency. And other wavelengths the atmosphere will block, so therefore a satellite cannot detect those other wavelengths. So you can see visible light easily passes through, certain wavelengths of infrared passes through, but other wavelengths such as X-rays and gammas do not pass through the atmosphere effectively. And again, this is showing us the atmospheric window, just a different way to represent it. You can see visible passes through the atmosphere very nicely where other wavelengths are blocked. One of the common questions that you hear a lot of times from students are, why is the sky blue, or why is the sunset red? And this has all to do with scattering of visible light by the atmosphere. During the daytime, when we see the blue sky, the blues are scattered more than the reds, light scattered, so it looks like it's coming from multiple different points all over the sky. And then the red is because the blue is scattered outside of our visible range by the atmosphere, and only the reds get to our eye as the sun is appearing to pass below the horizon. Remote sensing is not a new science. It has been around for a long period of time. It actually did start with pigeons and hot air balloons. We actually had pigeons they strapped cameras to that actually was used to fly and bring back the camera, and they developed the film. So into the 1960s, even into the days of satellites, we were using film for remote sensing. We had satellites that would actually send out a module that contained a roll of film. It was picked up by Air Force airplanes, and then they'd bring it back to process it. As we moved into the 70s and 80s, we start doing solid state detection and no longer doing detection with film. And as we move into the 90s, it becomes almost completely solid state detection of the wavelengths. And as we move into the 2010s, we're now seeing unmanned aircraft, but this unmanned aircraft is now terrestrial based and not any longer orbiting the Earth. So you can see these changes in the remote sensing. The concepts are still the same: gathering of electromagnetic energy to understand things about the surface of the Earth. So as I noted a moment ago, solid state detection devices are what we now use. Think of the solid state detector as a photon counter. Every time a photon enters, it notes where on the grid that photon entered. These are black and white devices, so we have certain devices that are sensitive to red light, others that are sensitive to green and to blue, and we might use filters as one of the ways to help on the sensitivity. But as the photon comes in, it's noted where on the grid it strikes, and we basically count the number of photons with our solid state detector. Most of our remote sensing that we do is passive. By passive, what we're doing is we're collecting the reflected, re-emitted energy from the surface of the Earth. We're not making it active, because active would mean that we send a pulse of light to the surface of the Earth and see the reflection in the re-emission. Let me give you an example. If you take your cell phone camera and take a picture, that is a passive use of remote sensing. It's because what you're imaging, you're not in direct contact, you're looking at the reflected and the re-emitted energy coming from whatever you're taking the picture of. But if you turn on the flash on your camera, that flash sends out a pulse of energy, strikes the object, and sends it back to your camera to be detected. That would be an active type of remote sensing. So therefore, if we're doing LiDAR, where we have an aircraft flying, sending pulses, laser beams, striking the Earth, and we're looking at the reflection of it, then that would be an example of active remote sensing. But most of what we do is the light reflected from the sun by the Earth, or re-emitted by the Earth back into space, or detected by an aircraft or a satellite to make our measurements. One of the things that we have to worry about is the resolution. So obviously, if I have an aircraft that's at 100 feet, I might have a different resolution, depending on the camera that I'm using, than if the aircraft is at 5,000 feet or is at 50 miles or 100 miles high. So the size of what every pixel, the pixel being a picture element, the size of each pixel determines what the spatial resolution we have is. So let's take an example. Here is a Landsat image, which is a 30 meter by 30 meter pixel. Very, very little can be understood at this resolution. You cannot really pick out things other than maybe a roadway running through here, and maybe this is a building right there. It's hard to tell, or maybe it's a parking lot, but real hard to tell. If we increase the resolution of the camera now to a 10 meter resolution, you can start to see a little bit more detail. This is an image of the same object that we just looked at, but this is a Sentinel image versus a Landsat image. So this is 10 meters on a side. So therefore, if you think about a football field, there's basically 10 picture elements in the length of the football field. So you can start to see a little bit of detail. If we increase the resolution again to about 1 foot resolution, so now we're going from 10 meters to 1 foot. Now you can start to see the buildings very obviously, the parking lots, and even the cars in the parking lot you can see. This is the location of the National Geotech Center, the southwest campus of Jefferson Community and Technical College. So here we're at about 1 foot resolution. Obviously, as our resolution gets better, we're seeing a lot smaller area for each pixel. Therefore, if we want to look at the same area, then there's going to be a lot more pixels in this image than there was in the first image, which makes it interesting when you're doing processing. This is a 6-inch image. Now you're starting to really see the different parts of these buildings. You can see the sidewalks, the lights poles even start to show up as we look at it. So we're seeing a lot finer resolution. You can see the trees. This happened to be flown when there wasn't any leaves on the trees in March, but you can see what's going on. And if we continue that to 1/2-inch resolution, now you're starting to see very crispness in a very small area of the entire view that we were looking at before. You can see every street light. You can see the units on the tops of the roofs. you can see that for safety reasons, our buildings have wrote onto the roof what building they are, the name of the building, and so on and so forth. So we went from a half an inch as the finest resolution we have to starting with 30 meters. So just in one 30 meter pixel, that's about 90 feet, we've got 90 times 12 times 2. So think of how many more pixels are in a half inch resolution versus what was in a 30 meter resolution. So to have that same coverage of 1 pixel from a Landsat satellite, that same image size would represent lots of pixels when we're looking here at half inch resolution. So that's spatial resolution. Temporal resolution is how often do we sense the area? So with something like Landsat has a polar orbit. So if we think about it, the Earth is turning on its axis and the satellite's going around the poles of the Earth. And so about every 16 days, the entire Earth is imaged. So that's fairly constant images. Something like a weather satellite, while it is orbiting the Earth, it's orbiting at the same rate as the Earth is turning and always appears to stay over a certain area of the Earth. So maybe over the eastern half of the United States, so that we're looking at the satellite imagery of what the weather is over the eastern United States. Other devices, just low-flying aircraft and unmanned aircraft, do not have a very good temporal resolution because that is usually created on demand and not constantly being flown. There are some exceptions to that, but that's generally a low temporal resolution. Radiometric resolution is how good is the data. So if my chip that we said, think of it as a grid, has a depth level of 8 bits, that means it can sense between 0 and 255. So the more photons, the larger the number. Well, we have therefore 256 unique divisions. If I change my sensing chip from an 8-bit chip to a 10-bit chip, now I go from 256 divisions to 1,024 divisions. Thus I have much better variance in the brightness, if you will, of the object. And we can go 16-bit, and obviously that's going to be a much bigger number than what we saw with 8 bits. And if we only went with 1 bit, it'd be either on or off, black or white, and there'd be no real difference between just if a photon was received or if it wasn't received. So we have these different ranges. So the better resolution from a radiometric standpoint, the more depth we have in the chip. And finally, we have spectral resolution. As I noted before, a lot of the chips are 3-banded. So we have a blue area, a green area, and usually a red area, something like this. So those are our 3 bands: red, green, and blue. And so with those bands that we are looking at here, we don't have a lot of variance. It's either red or not red. If I instead broke the blue up into 2 blues and maybe broke the green up a little bit here and had a couple reds and maybe picked up a little bit of infrared over on the side here, now we have a better spectral resolution of what's going on. So we go from 3 bands, and then if we add near infrared, 4 bands, to maybe having 8 or 10 bands, and therefore we have what we call multi-spectral, and we can understand what's going on with the reflectance and the re-emitted light much better. The reason this is important is each item has a certain spectral resolution. So if I had on a red shirt, I'm going to emit a lot of red energy, but very little green and blue energy. And so what we're looking at here is a graph of wavelength. So the blue end of the spectrum is down here, and the red end of the spectrum is up here, about right there. And so this is near infrared over here in the 800 area. And we can see that vegetation has one spectral signature, and turbid water would have a different spectral signature, and so on and so forth. If I only have red, green, blue, or if I have red, green, blue near infrared, that limits a little bit on how good of a signature I can have. But if I have a multi-spectral camera that maybe breaks it up into 10 bands instead of breaking it up into just 4 bands, then I can identify things better. To the level of identification that we can, by looking with Landsat data, we can determine if this field is corn, or if it's soybeans, or if it's wheat. So just by looking at the spectral signatures, you can make those determinations. Is it water, or is it asphalt pavement? Again, by looking at the spectral signatures, you can determine what the substance is that you're getting the reflected energy from. Again, think of it as a grid, and from the grid we have part of the grid associated with the blue, part with the green, and part with the red. But if instead I had another grid here and another grid here, that's going to give me more detail as I look at what's going on. So this is Landsat showing the different bands that Landsat has and the different wavelength areas. And so we got blue, green, red, near infrared, infrared, and down into the thermals that we have. And these are the wavelength families that are associated with it. In Landsat 8, there was slightly a change in the numbering schema and the bands that were available to us, as that satellite, being a newer satellite, had this coastal blue in it, which is good for water detection. That wasn't there previously. Notice the resolution being about 30 meters of each of these bands. Sentinel, which is European satellites, had slightly different band areas, and this is represented slightly different than the previous slide. These are the central wavelengths. They don't look at the extremities, and these are also 10 meter bands, notice, but they also have this coastal band like we just saw in Landsat 8. And so we can combine these bands in different ways. So if we look at 432, well, 432 would be near infrared, red, blue. I'm sorry, red, green. So NIR, red, and green. How do I know that? Well, we can go back and look at those slides just a moment ago. Well, the NIR is invisible to my eye, so to maybe be able to represent that on a computer screen, the way I do that is I assign NIR to being the red band. Red now becomes the green band, and green becomes the blue band, and we don't look at the blue band. So you can see some of the false colorings that we can do. So here's a 432, red, green, blue from Landsat 8, which is different band numbers than Landsat 5 and 7 were. 543, that's the near infrared area. 542, that's near infrared, red, blue, brings out water better. 765. We'll stop at this point. Again, visit the hub site to get more information and also to be able to download content and watch some videos and things like that.